IFU Cube Fitting for the JWebbinar 20. In this notebook, we are going to work on continuum and emission line modeling of an AGN in cube space. For this one, we happen to be working on NIF's Gemini data of NGC 4151, but similar analysis should work for the various cubes that you might get from the web. Okay, we're going to move quickly. We can spend more time definitely during the JWebbinar, but this is just as a backup tutorial. The first thing that you want to do is import all your packages and make some basic definitions to the data set. We do a quick look in matplotlib. All right, everything is loaded up. And here you can see we are going to visualize our data inside of QViz. All right, this is our AGN, and what we're going to want to do is define a couple regions. First, we want to define a region, a subset of the nuclear core. You can see that show up in red. We're able to take the wavelength slider and move it back and forth, and you can see some red shifted and blue shifted features appear. Okay, there's a blue shifted feature and there is a red shifted feature. So we are going to want to analyze those two features separately. So we're going to want to create two new subsets. All right, here's one, and here is the other. We can zoom in just a little bit. And we also want to define some spectral regions for analysis. This is the region of interest that we're going to want to analyze today. I just know that because I've been working with this data set for a while. But we also are going to want to define a background region, background continuum that we're going to want to remove, okay? And we're going to want to remove that from every single spaxel. And so the way to do that is I need to remind myself of the names that I use. Okay, going down all the way here, we'll come back. All right, that's going to be our final name a little bit later. Okay, and we're going to want to use what we call model fitting, and we're going to want to fit the collapsed spectrum for the entire cube, this black line, okay, but only over subset 5, which is our background region that we've defined. And we're going to want to do a linear fit, which is L, so we can edit the defaults if we want, but we're going to use the automatic fitting routine and it's probably sufficient. So here is the equation editor. All we're doing is fitting one parameter at this point, one model, and we're not fitting the entire cube, we're just fitting the collapsed spectrum at this point, which is called linfit, and we will fit that. And you can see that's a pretty good fit for our continuum that we want to subtract. So now we want to fit the entire cube, and we're going to call that linfit cont because that's what we are going to extract later. We already saw that variable name. We're going to plot the model of that linear fit over here. So remember, what we're doing is we're creating a cube of the spaxel by spaxel fit to the background region, and that is our result. Okay, now these two cubes are now linked in WCS space, but this is just a continuum. There's no line emission, okay? So what we're going to do is we're going to scroll down here. This is just some extraction. We're going to extract the different regions from our visualization tool, which allows us to continue our workflow. And here you can see our blue shifted and red shifted components. Going down here, we're going to extract the regions again. We already did that. This extracts them a slightly different way. And then we are going to extract our model cube. And what we're going to do is we're simply going to subtract that model cube from our original science data. Okay, simple as that. It's just a simple subtraction in cube space. Okay, we can also get the parameters from our fit if we want. Okay, our slope and our y-intercept, and then we're going to plot our continuum subtracted cube back into QViz. All right, there you go. So now, if you look at our collapsed spectrum, it's a lot flatter than before. So we did a really good job. We should be pretty proud of ourselves. And now what we're going to want to do is analyze the spectral component here. It's a multi-peak component, and this is pretty cool because we only care about one of the peaks. Okay, this peak all the way to the right. We want to subtract the other Gaussian components. So this is really a little bit more tricky, but it shows you the advanced nature of CubeViz. Okay, so what we're going to do is, again, we're going to fit the entire cube and over subset 1, and we're going to have 3 different Gaussian components. And I'm going to add them one at a time. Okay, so I'm going to add Gaussian 1, and down here I give some cheat sheet notes because I've done this before and I played around with it long enough to know that these are the values that we're going to want to make as our initial guesses. Okay, so let me just fill these out, and we're going to fix them as we add each component. Okay, G1, right? And we're just going to call this fit G1. Okay, show in spectrum viewer. Voila, that's a pretty good fit for G1. Okay, now we're going to add a second component, and we're going to call that G2. And again, because I know what the answers are supposed to be, at least closely, I can add this, and I can fix the value, and I can fix the mean to be about 7. And actually, I think I want to be at closer to 90, if I remember correctly. And we are going to now add G1 and G2. Oops. We're going to call that G1, G2, and we're going to fit. Oh, where did it go? I have the wrong values here. This one is supposed to be that. This one's supposed to be that. And we'll let that one float. Sorry about that. We will do another fit. Let's see if that works better. All right, so you can see that's a lot better. And now we have 2 different models here, G1 and G2. But we want a third component, okay? So we're going to call that G3. And again, I have my cheat sheet. Here we go, G1 plus G2 plus G3, and we will do that, and let's see if this works. All right, pretty good. So we can actually turn that off. We can see our combined spectrum. Now I fixed it. We want to actually optimize that fit. So here's what we're going to do. I'm going to turn off all of those, and I'm going to call this Gauss fit. Watch this. Oops. Now I'm turning off the fixed values. Now I'm turning off the fixed values. All right, we're going to call this Gauss fit. And let's see how we do. Oh, beautiful. You see how beautiful that is? So, if we're happy with that sort of fitting, we can now fit the entire cube, okay? And let me just see what I call it when I pull it out, right? That's important. And I call it Gauss all cube. I need to change that value there because I just named that incorrectly. All right, and we're going to plot that just like before. And here we go. Now we have to let it fit the entire cube. And again, what we're trying to do is remove these Gaussian components so that we're only left with the line of interest. I forget which line this is because this is not my science, but it is that line of interest. Alright, so we're fitting the model to the cube. And it takes a while. We're doing a multi-Gaussian fit to the entire cube. Alright, so that is pretty standard. If you have more cores, this can run a little bit faster. This is for a single core. Alright, there you go. If you want to play around with the settings, you can, but I've done this enough. I'm pretty confident in that fit. And now we are going to extract our fits back into our notebook. And we need to sometimes get these in the right shape. And we're going to subtract the model of the two Gaussians from the original data set so that we're only left with the resulting flux from that line of interest, if that makes sense, okay? All right, so we're going through spaxel by spaxel and we're subtracting this off the original data set, okay? And here we go. There's our total background plus our Gaussian 2 component. And here it comes, the original data minus the model. And let's take a look at what the final data set looks like. All right, here we go, getting everything in the right. Oh no, see? Alright, it looks like one of the data sets is not correct. Give me one second to confirm that up at the plotting. But here's the real point. If you scroll through wavelength space, you are now only looking at that line feature, and you'll see that redshift and blue shifted component pop out big time. Boom, boom. Okay, much better than before because we're only looking at that line. All other continuum and Gaussian components have been subtracted off.